So welcome to another MTH129 Discrete Maths um, online meeting with a smaller pen. So this tutorial, I just want to complete the topic on graphs. So in particular, I want to look at trees, which I'll just do one example, and then some algorithms on weighted graphs. That's what I want to focus on. So the first example I want to look at is a binary search tree. And so binary trees are underlying data structures but useful things. And so binary search tree is just a good example of one. And you could use them to sort stuff data. Essentially, a quick sort algorithm sort of does the same sort of stuff, though it does it within an array. It does it inline an array effectively. And so therefore, it's plagued by similar issues to a binary search tree. But anyway, let's just have a go and we'll see what some of the issues are. I won't do the whole thing, but I just want to get the idea. So I've got a bunch of words. So these are, if you know them, they're the Pokemon names from the original Pokemon game in the order in the Pokédex, if that means anything to you. So a bunch of names. So what I want to do is I basically want to put them in alphabetical order, essentially. And so I need to sort them out somehow. And so one way of doing that and permanently storing them in order is to insert them into a binary search tree. So you get the first name and you insert the tree. So there's nothing in the tree to begin with. And so when you first edit the tree, it becomes the root node. So that one's done. Then we want to add the second one, Ivysaur. So you compare Ivysaur to the current root. If it's less than, in this case, less than alphabetically, we'll chuck it to the left. If it's greater than alphabetically, we'll put it to the right. So in this case, I becomes after B, so we'd put Ivysaur, just around I, here onto the right. So then the same sort of process happens at a time. So to get the next one, Venusasaur, how you pronounce it, you compare the V and the Venusasaur and Bulbasaur and go, well, that's bigger, so you head right. Venusasaur is bigger than Ivysaur, so you head right, and you keep going until the direction you want, until there's nothing there, and if there's nothing there, create a new node with the value you want. So we put Venusasaur here to the right of Ivysaur. Let's just do, say, two more. So with Charmander is bigger than Bulbasaur, so you head right. Charmander is less than Ivysaur, so you head left. And there's nothing there, so we create it. So you have to create a node which contains Charmander. And the last one I'll do is Charmeleon. So Charmeleon is bigger than Bulbasaur, so head right. It's less than Ivysaur, so head left. And it's bigger than Charmander, so head right. Nothing there, so we'll create a new node. And you can keep going, and you could add the other ones in a similar sort of way. So some things to notice with this is just happens to be the order from the Pokédex is that because the very first one happens to start with B, which is the second letter of the alphabet, that we have a very unbalanced tree. So we've got everything here is on the right subtree, and there's nothing in the left subtree at all. And so as a binary search tree, it works more efficiently if the depth of the right and left trees are about the same. If they're not, then you can sort of slow it down. So balancing is important. Pardon me. So having a self-balancing tree works better than this. And essentially, when it comes to a quick sort, so quick sort's a way of sorting out data. It's a different algorithm. But basically, how quick sort effectively works is it ticks a partition point. So which in this sort of picture amounts to picking the root node. So just uses some sort of heuristic to work out what the root node would be, and therefore anything that's bigger than that will become the right, and anything smaller that will be in the left. And so picking that partition carefully, and so one simple application of picking the what should be the root node is just the last element of the array, for example. That's just a quick way of doing it. That becomes the root node. And as you can see here, or I've picked the first one effectively, that if you just pick the first and last, if the data's already sorted out, or if you happen to get the last case, you can get a very unbalanced tree. And so there are improvements to quicksort, which make a better starting point. So one that's closer to the middle, so hopefully better at getting it balanced. But it's the same sort of issue. So understanding binary search tree is actually useful to understand quicksort, which is a very popular algorithm, and the reason being is because it's quick most of the time. But if it's unbalanced, it isn't. So the downside of quicksort and binary search trees in the same way is that if you happen to give the keys in the wrong order, you can get some pretty dodgy looking. You get a dodgy looking tree or a slow algorithm effectively. But anyway, what I want to do is I want to look at when you've got a tree, how do you traverse the tree? How do you visit the nodes? So essentially you want to loop over the tree in certain ways. And there's different ways of doing it, and different applications have different things in mind. So one is called a post order. So the way to do any transversal visually is basically you start at the root node and you just sort of do a little path around all the nodes like that. So you start at the beginning and then you finish at the top. So you sort of circle it all. So for a post order, visually, that basically means you basically visit the left child first, and then the right child, and then you lastly do the parent. So visually, that really means when you're going around, you visit things as you touch them on the left. So visually, and I'll explain how it works in a second. It means as you pass the node on the left is when you do it. So if you go around this path, the first left-hand side you meet is chameleon. So that would be the first one. Then you come back, Charman is the next one in a post order. Then you hit Venusasaur, and then Ivysaur, and then lastly Bulbasaur. So that would be a post order for this particular tree. How it works otherwise, so in terms of if you program it up, it's a little differently. So how it works programmatically, a post order, you look at the root node and you're going, well, I would do the left subtree first. There's none of it, so it's easy. Then you do the right subtree next, so all of this thing here, and lastly you do the parent, which is Bulbasaur. So Bulbasaur would be the very last thing, which matches the 5. And then you do the left, then you do the right subtree, and you do the same sort of thing. So when you're up to Ivysaur, you're going, well, first I had do all the children first, starting from left. So you go the left children first. With Charmander, I'll do the children first. There's no left to do, so I still do the right child first. So you do Charmeleon very first. That's the one. Once you know all the children, you go back to the parent. Now that I've done all the children, that I have to do the parent next, so I do it after all the children. That's the post idea. Head back to Ivysaur. I have to do all the children first, so I'll do Venusasaur before Ivysaur. And that's the order. So you can see it. So programmatically, when normally you just know links, it's easier to say, I'll just do left, right, parent. But visually, you can just draw this sort of path and hit them when you pass on the right. For an in order, you can do the same sort of trick. Again, do this path. And when you touch at the bottom of all of these things, all the different nodes, is when you visit them. So for example, when you're going along, the first one you come in is Bulbasaur. So that'll be number 1 in order. Next one you touch the bottom of, which is Charmander, I should say. Then Charmeleon. And then going around, you hit Ivysaur. And then lastly, Venusasaur. That would be what it would be in order. And so how these binary search trees are designed is that the in-order traversal gives the nodes in alphabetical order. Well, in numerical or whatever the order you want. So you can see Bulbasaur, Gemina, Charmeleon, Ivysaur, Venusaur are now in alphabetical order, which is the reason why you would use such a tree. But that's just showing you a visual way of being able to write it down. And so since you're mostly going to focus on using drawing these trees on a piece of paper for this subject, that's a useful technique, although programming might be differently. So in your assignment, you're looking at some trees, so expression trees as well there from memory. And so just the traversals are the same sort of idea. And so in order makes sense for a binary search tree, whereas for an expression tree, all three orders have some meaning to them, etc. So that's a bit about trees. And so make sure you do assignment 3, looking at those questions. I'm going to ask if you got them. Next is, let's find the questions. So other things I want to look at is weighted graphs. And so there are a few key algorithms that I want to consider. So the one that's, I think, so there's the minimal spanning tree. So I think that's the one that people is the easiest to understand. So I'll leave that to last if I have time. The other two are the maximal flow and the shortest path. They're the other two. So I want to focus on maximal flow. So I think this is the one that is least understood. I mean, up to you, and you might go, oh, yeah, I understand it completely. So this is my graph and my picture. So I've got a graph. Basically, I've got a bunch of irrigation canals, and it's got a slope to these canals, so the water flows downhill, and so the water will flow from A down to C, for example. So I've got a starting point, and a finishing point, and I want to see how much water I can get from the top of my hill, so a dam or whatever it might be, down to something to where I don't know, animals want to drink from. So irrigation is more for cropping, isn't it? So I'm down to some sort of paddock I want down here probably to irrigate it. So I want to know what's the total amount of water I can get down the bottom here. So what's the maximal flow, essentially, I can get from the top to the bottom. So that's the question. So a key algorithm to do that is the algorithm by Ford and Fulkerson. They're the one of the early ones to develop it. It's still pretty good, and doing it by hand works quite nicely. So there are two ways of writing it down, and I want to show you both. So I'll start with the way that's mentioned in the study guide, which I think works in most cases, and then I'll mention an alternative, which is a good alternative to understanding some things. So what I'm going to do is I want to keep track of what I'm up to. So I want to relabel all the edges by how much flow I'm using so far and what's the total amount I can use. So to begin with, I'm going to have nothing in the network. So pretty much I have the first number, so 0, is how much flow I'm using, so nothing at the moment. And the second number, so 30 in this case, would be the flow I could use. So you can just say I'm just adding 0 everywhere to all these different paths. And go from there. And that's the starting point. So that's just setting it up. Next thing I want to do is I want to pick a path to push the flow through. So pretty much so you just got to pick a path. And again, you want to put some working over here. So for your assignment and exam, if you have a question like this in the exam, so you want to pick different paths and a flow along it. So Dylan, pick a path. So what's a path from A through to B, where you can just follow the arrows, where we can get some sort of flow happening? Which one would you pick as a starting point? Yep. So A to C to D to B. Sounds pretty sensible, just going all over the top there. So what you need to do is you need to look at the spare capacity along each of them. So the spare capacity is the amount, the flow along that edge, so 30 in this case, minus how much you've already used. So the spare capacity on A to C is 30. The spare capacity along C to D would be 15 minus 0, 15. And the spare capacity along D to B would be 35 minus 0, would be 35. So they're the spare capacities. You pick the smallest of those because that's the most you could squeeze through. So the maximum flow along that particular path that we could do left would be 15. So we've got our 15 and we've got to basically then push that 15 um, along our path. Oops. So we've got 15 of the 30 originally used, all 15 of C to D, and 15 of the 35. And then repeat. So basically we're going to find another path. So what path would you pick next? Okay. So your first one was going around the top. Next one you picked is go down the bottom. Sounds pretty good. So again, you look at spare capacity. So you got A to E to F to B. You got 30 spare capacity here, 5 along the bottom one, 20 along the last one. So the spare capacity is 5. The minimum spare capacity along them is 5. So that's the most we could get flowing along this path. Any extra. And so then we just add 5 to each along that path. Now we need to show some working. So different ways of showing working would be to write the whole graph out a second time below it, so people can really see what you're doing. Otherwise, just show, look, this is what I'm doing at every point in time, every step. So I've added this path. I want to know what the flow is. That's what I've put onto it. Now, for an assignment and an exam, if you get it all right, it goes really nicely. But if you made a mistake, like if you make a mistake here working at that flow there, and you put it all in place, sometimes it's hard to see that. And so I'd encourage you for an assignment, and indeed the exam, is to write the diagram a few times. Maybe you could combine a few steps in one graph, so maybe do 2 paths at a time perhaps, if you want to save some space, certainly in the exam. But try to do it more often, just so if you do make a mistake, it's really clear in the markers, oh, that's just 1 mini thing, and they'll give you the rest of the marks. Just a bit of a word of advice. Okay, so we've got 5 along the bottom. So incidentally, you can see that the top and the bottom edges here are both already full, so we have to use something different. What path would you pick next? You've started A. So A to E to D to B. So for A to E, you've got 30 possible, already used 5, so there's only 25 capacity left. So only 25 left. From E to D, there's a full 25 I can use, and from D to B, I've got 35 minus 15, or 20 available. So lots on that path, and again, you want to add that to the path. So I've got 5 already. I want to add another 20 to give you 25. I've got 25 on E to D. Not 25. I'm only pushing 20 here, aren't I? So 20 from E to D, and another 20 from D to B, so that will give me the full 35. And again, it's good just to note to ourselves, okay, that path's now fully taken, so I can't put any more on that path. And so therefore I can avoid it. What path would you pick next? And again, I can do some things. So it's got to start at A. I can't do DB, so it's got to finish with F and B. So A to C, FB would be a nice simple one. So A to C has got a spare capacity of 30 minus 15 of 15. C to F would have spare capacity of 10 minus 0 of 10. And F to B would have spare capacity of 20 minus 5 of 15. So the smallest of those is the C to F1, which would be 10. And then I can pump that on and just add that 10 to each of those. So we're getting there. So you're thinking, well, I still got, the question is, can I find another path that can give you any more? So can you think of see any more paths? So if you look at it, there's still a little another 5 capacity, so I still can do something finishing the F to B. C to F's full, so really isn't available. And so just like you rightfully said, there's not many options getting a bit slimmer here. So A to C to E to D to F. That's pretty much what we've got to do. Just to avoid all these full paths. So from A to C, we've got 5 spare capacity. From C down to E, you got 10 spare capacity. From E up to D, you got 5. From D down to F, you got 10. And from F to B, you've got 5. So 5 is the smallest, so that's the most we can push on that path. And just add 5 along that path. So we've got the full 30 along here. We've got 5 from C to E. Full 25 from E to D. We've got 5 going down and 20 over here. Can you see another path that's available? So can we do it again? The answer is no. And again, you can see that for a few reasons. The easiest way to see it, I reckon, is to say that F to B is now full. So both the paths going into B are full. So there's just, no matter what I do elsewhere, there's no way I'm going to get it into B here. And so therefore we're done. So we're done. And so then we can work out total flow a few ways. We can add up our numbers. It might be easiest to focus on B. So with B, we have 35 plus 20 going into B. So we have a total of 55. So the maximal flow is 55. And that gives us the answer. So when things go nicely, that works out quite well. You can do some other things with these graphs. So I just want to consider this sort of thing. This is a bonus sort of question. Suppose we go, well, 55 is good, but can we make it 60? Like, if you think about it, the amount of the channels flowing out from A, if you use 30 plus 30 would be 60. So there's a amount of flow from A is 60. Can I change an irrigation channel somewhere to make the total flow up to 60? And let's see, can I do it with just one irrigation channel even? So the way to do that is to look at is the idea of doing cuts. So look at all the different paths which are completely full. So I've ticked most of them already. So the other one I haven't ticked is this from E to D, which has got the 25 capacity. So that's the only one I haven't ticked yet. So basically you can see I've got 6 different paths here. And C to E's got 5 out of 10. So that's not full yet. I don't think so. Yeah, so I've basically got 6 different paths here which are completely full. So what I can do is I can draw a line or a curve sort of thing which passes through these and none of the other edges to cut the graph, to cut this graph. So one cut I can do is going down here. So this cut here would pass through these 4 edges which are all full, and that breaks the graph into 2 parts. That's called a cut. And again, anytime you've got edges which are all full, you can make another cut. So there's another cut I could do over here, for example. That'd also work. Now, with each of these cuts, they have to basically pass through edges which only are full and can't pass through edges which are not full. So as you can see, I've drawn 2 cuts here. you can cut the graph in lots of different ways, but these two cuts here, so you can divide the graph into two ways, lots of ways, but these sorts of cuts as generated are called minimal cuts. Let's get the and so the total flow through the minimal cut, so this would be 35 plus 20, for example, is 55. So the amount of total flow through a minimal cut is equal to the maximal flow. That's one of the nice results. So you got 15 plus 25 plus 10 plus 5. If you add them all up, you get 55. So any cut, the flow through that cut gives you the maximal flow. That's another way of doing it. The easiest way to find minimal cuts is to find maximal flow directly. But it does tell you a few other things. So it's on these useful things is essentially these minimal cuts really show you where the bottlenecks of the whole situation is. So the places where you just can't get anything more flowing through really is on these minimal cuts. So you're always going to have at least one minimal cut. Sometimes you can have two, like you can see here. And so if you want to try to get more flow through the whole system, you really have to increase the flow through each of the minimal cuts. So in this case, we've got two of them. So the only way of getting more flow through the whole system would be to actually increase flow through both of these, which require not just one irrigation channel, but two. So the question was, can we increase the maximal flow by increasing flow along one irrigation channel? And the answer is no. And the reason is because it's got two minimal cuts. So you can do advanced stuff with forward focus in the algorithm by looking at these cuts afterwards. And so we can increase the flow by doing two edges. So you just you have to do the flow across two of these cuts. And so, for example, if you made C to D and D to B, if you increase both of those by 5, then you can increase the maximal flow to 60, for example. You'd have to tweak it a little bit at the front here, but you could do it. Now, you can't get anything more than that because, producing another minimal cut over here at the front. So that's a more advanced idea with forward and focusing. So just want to show you, okay, another sort of thing. So this is the same picture. So this is the same graph, but if you've chosen different paths along the way. Just to mention some other sort of concepts for it, and this is certainly the hardest part, so I want to do it two different ways to try to explain. So this is choosing, so you've chosen some different paths along the way, and you can see we're up to a certain point in time, and you can see that there's still a bit, there's some of them are full, but there's a bit of spare capacity on D to B. So what I need to do is try to find another path which I can pump things from A to B. And so the only path going into B which has got spare capacity is D to B. So any new path will have to go along here. C to D, E to D, and C to F are all full. So the only way, again, of crossing the middle part here would be going from E to F. To get from A to E, you can do lots of ways, but the simplest is just directly. So that's fine. So pretty much if I got any more paths I could try to pump things through, I'd have to go along these ones. And so I have to join F up to D over here. Now, at first glance, it seems like I can't do it. Because the only edges going out of F go to B directly, and that's already full. So it seems like you can't do it, but you can. So this is the trick. And that is you can go paths backwards. So this is the path, but you can go in the opposite direction, like this. This is our special case. So you can go backwards if you've already used that edge. So pretty much you've got a flow of 10 already. So I've already got a flow of 10. So I can subtract from that. So you can go take paths backwards and subtract flow if there was already flow along that path. So this is the trick. So to work out the spare capacity along here, I'll just write them down. So the spare capacity on the first one's 5 and 5, and the last edge would be 5, so like before. Now this one edge here, the spare capacity along here is, well, I have 10 flow already. I can subtract up to the full 10. So the spare capacity in that sense would be I've got 10 units I can take away. And so essentially what we're doing here is instead of adding more flow, what we're doing is reducing the flow that's already there to balance it all out. And so on this particular path, the smallest spare capacity would be 5, and so I could pump 5 along this particular edge. And so what that would look like after doing that, I have 30 along at E, and I have 5 from E to F. And now I'm moving 5 along here, so that would reduce this 10 to 5, because I'm just really subtracting it. And this 30 would go to 35. And when I do that, then the amount of flow into B is now full. Then that's the end of the algorithm. And again, this graph looks very similar to the one we worked out a second ago. It's not quite the same because the flows between the beginning here are a little different, but it's equivalent. And in particular, we found the same maximal flow. So that's a bit of a trick. It's an advanced technique. Now, not everyone likes that. They don't really like the idea of negative flows. So I just want to show a different way of writing down Ford and Fulkerson's technique. So you have you have your graph as before. But what I do is I write them down as undirected edges, at least for the moment. You need to know which ones were directed later on. So you've got basically you've got a bunch of undirected edges. So I draw it twice. Then when you do, then you label the edges in a certain way. So how we do it is you write on every edge, you write down 2 numbers, one at either end. So you got A to C, that's one edge. So you're going to put numbers on either end. So on each end, you've got how much. So to start off with, so the original edge we had 30 on here. The edge, and near A, you basically put how much you could potentially push along the edge. So in this case, it's 30. So I could put up to 30 along the edge. And at the other end, you have how much flow you've already been using, which in this case would be, well, nothing to start with. And you label all the edges the same way. So I'd have 30, I could go from A to E, and there's nothing going backwards. From C down to E, I could put down 10, I've got nothing going so far, etc. So pretty much it's the same, it's labeling it differently. It's the same algorithm, ultimately, we're just labeling it differently. And the diagonal is the hardest one, so you don't lose track of what's happening. So 25, 0, 10, 0. So basically, it's labeling all the edges at twice, and you've got, and so how does this match up to what we've labeled before? Well, basically the number at the beginning is the spare capacity that we have in that direction. So when doing any path from A to C to D to B like we did before, these numbers just now represent the spare capacity and just pick the smallest of those. So when you got up to, and so what we do is to go from any one time, you basically would move one number from one end to the other. So along this top path, the minimum spare capacity was 15, like we said before. So we moved 15 along. So we would subtract 15 from the first number and add it to the second one. So we're basically reducing our spare capacity to 15, and we've now got a flow of 15 along, etc. You do the rest of it along as well. That's how it sort of changes. So when you're getting to this, if you ever got down to this stage, what it corresponds look like is you've got 5 spare capacity along A to C with a flow of 25. Let's see if I can do the rest of it. So, 5 spare capacity with 25 going on it. From C to D, I've got 10 spare capacity with 0 being used already. From C to D, got no spare capacity, all 15 flowing on it, etc. And here you've got 10 being used, so that would be 0. Okay. Let's just finish this last one. So you've got 20, so you've got 5 left and 30 being used already. So that's what this picture corresponds to. So it's just a different way of labeling it. And so to work out the total along an edge, you just do 5 plus 30. 30 would give you the total weight for the edge, for example. Now, what you do to find pass at this point in time is you don't have to worry about the edges, the directions, which is what, when you're doing this sort of trick I did before, it's the directions really get in the way. And you can see the numbers here just represent how much you're going to push along. So again, if you're going from trying to go to B, well, there's a 0 here, so you can't have that one. So I can pick the edge from B to B because there's a 5 I can push things along. And again, like we said before, I can go from E to F because there's a spare capacity of 5 along here. And I go from E to A to E because there's 5 along here. And when you're looking at the edge from F to D, I can see I've got a 10 here already. So I can use some of that 10 to push things along. So what I like about this second way of writing it down is that when you do have to go in the opposite direction, then these numbers just go, I've got 10, I can just use some of that 10 to go the opposite direction. No worries. And you don't really have to think about it, and the trick doesn't seem problematic at all at that point in time. And you go, like, I've got spare capacity of 5, 5, 10, and 5. Smallest is 5. I can now push 5 along. And you would get the end and be able to resolve this sort of trickier case. So that's one thing I like about it. The one thing I don't like about this notation is there's a lot more numbers to write down. And as you can see, it's it can get complicated because it's hard to know. Well, I've got 4 numbers all floating around C. It's good. You have to be careful with how you write it down, not to confuse yourself. That's the downside to it. So both go. So they're both worthwhile knowing and considering which one you find easier to do. So some thought there, and just a way of trying to overcome some difficulties people have with that. And as you can see with this example, although I certainly can manufacture a case where you have to do a reverse flow idea in that trick. The way we did it before, which was quite natural, we never got to that situation, so we never got stuck that way. And so it does depend on the choice of paths. So if you choose a different choice of paths, you can get in this sticky situation to get unstuck, need to get unstuck with. But you can never tell until you really do it. So that's some comments about maximal flow. And as I said, it's useful for various algorithms, various sort of applications. So the other sort of harder case with if I find my question, the other sort of case that people find hard. So out of the weighted graphs, the other one that's the next hardest perhaps is the shortest distance. So what we're going to do is, shortest distance is basically you've got a graph, and you want to try to find the distance between 2 different nodes, or maybe the distance from A to every other node, and you can do the same idea. And you want to find the shortest distance. And as I remarked in lectures, if you've been listening, you could do that what you could do is the dots here could represent physical locations on a floor, and if there's something in the way, you can't. There's some places that are unreachable. Well, there's a settee, and you've got a sofa in the way, something like that. And you might want to use this. And the numbers here, the actual physical differences between the dots. And you could then do shortest distance to work out, a pathfinding algorithm. And you do that in a computer game as well, for example. Now, doing District's algorithm, or however you pronounce it, that's what I'm about to do, could be slow if you're not careful, and sometimes using heuristics to try to get real-time speed might be necessary. But let's have a look at how to do it. So what I'm going to do, I'm going to try to use District's method to find the shortest path between A and Z. So what I'm going to do is put some working down. So I'm going to put nodes visited over here. And I'm going to put something else, but I'll explain some more things. So how District's method works pretty much is for each, what we're going to try to do is you pick a starting node, so I'm going to pick A. I want to know the distance from A, the shortest distance to A, essentially. So above all the nodes, I'll write down my current estimate of what the shortest distance is. And so from A to A, I know this is 0. From all the other ones, I don't really know yet. So I'm just going to say the distance to all the other nodes, shortest distance is infinity, which is really just another way of saying I've got no idea at the moment. But as we go through, we'll get some idea. So we'll start with distances to all of them. So that's the starting point. That just sets it up. And so as we go through, we'll update these numbers to represent the shortest distance we know at the moment. Once we finalize it, these numbers will be the exact shortest distance from A to that node. But as you're going through, as it's a work in progress, they might be too big. So certainly infinity is certainly too big for D, for example. So then each iteration, you look at all the nodes which are not visited yet, which currently none of them are visited, and you pick the one with the smallest distance. So A, this is the moment, and then you mark it as visited. The way I do that visually is to color the node in. So I say coloring blue in class, because I chose my colors wrong. I'm coloring red today, but so that's the first node. So the first node visited is A. And then the next part of the algorithm would be, once you've got this node visiting this node, is you then via A work at this visited node. What's the shortest distance to all of its adjacent ones? So A can go to B. So I go from A to B. I've got no distance so far. Plus my 4 would give me a new distance of 4. If that number is less than what we already have, replace it. So we had infinity before. Now we have 4. That's better. That's our new best shortest distance. And going from A down to C, I've got distance of 3. 0 plus 3 is 3. That's certainly less than infinity, so I'm going to replace it. So what I'm also going to write down here in my working is distance has changed. So I've changed B to 4 and C to 3. So this is my working, essentially. And again, in an assignment, it might be worthwhile reproducing the whole picture multiple times, but I want to have some sort of indication to know what you've done. So that's the first iteration. So visiting one node and then working the distances from everything adjacent to that. Then you want to loop. Just repeat again. So then again, look at all the unvisited nodes, work at which one's the shortest distance. Which are the ones that we have not visited, which is the smallest number so far? Dylan? Yep, so C's got a 3 in it. So that's the smallest one. So we color it in to say we visited. That's our next visited node. And then for all the adjacent nodes we have not yet visited, we do the same trick. So A is already visited, so we don't need to go back. That's done, but we can go forward. So from C up to B is a distance of 2. C we said was a distance of 3, so 3 plus 2 is 5. So going along this path, we get a distance up to be a 5. That's bigger than what we already have, so therefore there's no point replacing it. So 4 is better, so keep the 4. But we have to do other ones. What about from C to D? Well, got the 3 plus my 3 would give you 6. And that's better than infinity, so we'll replace it. So we have changed D to 6. And again, from C to E, with 3 plus 6 would give you 9. In the same sort of way. So replace things as we go along. And then we repeat the process. So the third iteration would be find the node which is the smallest distance, which would be B. So I'm going to visit this one now. So I colour it in. And again, I'm going to push it on. So B here, the fact it's adjacent to A and C don't really worry because they're already visited. So the only unvisited one it's adjacent to is D. So we have to push the distance along. So if you do 4 plus 5, you get 9. 9's bigger than 6. And therefore, that's not getting anything better. So there's really nothing to change. So all we really have done in that stage is just say, we visited B, and I can't get any better. There's no better way around from that, so we'll just leave it. Then repeat. Next shortest one would be D. That's the next one that's the smallest. Because it's 6 versus 9 and affinities. And then again, push the distances. So from D to F has got a distance of 5. So 6 plus 5 would be 11. So now I know that my tentative distance from to F is 11. If you go D down to E, you got a 1. So 6 plus 1 would be 7. It's worthwhile just writing it down. So if we worked out earlier, if you went from A to C to E, you got a distance of 9. That was our shortest distance we knew at the time. But now we've looked a bit more in the graph. We can see if we go E to C to D to E, we actually get a shorter distance of 7. So we can see the shortest distance is actually not 9, but it is actually 7. And so we've actually revised our distances. So these numbers here, just it's worthwhile explaining, represents the shortest distance we know of at the moment. And as we visit more nodes, as you can see just here, sometimes we can revise them down. So we say, oh, we found a better way. That the shortest path was not direct, but going around a bit of a longer way, or visiting more nodes perhaps, but actually visiting more nodes end up giving it a shorter distance, which is good. And that's what we're really looking for. So we've got a 7 here. That's better. And then we repeat. And the same sort of things happen. So what's the next node you'd visit? E, yep. So color it in, push the distance, and the only edge that's left to go is over to G. So we change infinity to what? What distance would we put over on G over here? Yep, so 7 plus 5 is 12. And then repeat, so the next shortest one would be F. So you push the 2 down, so 11 plus 2 would give you 13. So you have 13 down at G. Well, we've got 12, which is better, and so I don't change that. And then if you go along this path, 11 plus 7 will give you 18. So currently, the whole idea is to work the shortest path to Z. So currently, the shortest path we found so far to Z is 18. The question is, can we do better? And we should keep going to see if we can find a better way. And so the next one we want to visit is G. That's the next one we want to visit. The only one that's not adjacent is Z. So if we push along, going via G here, what's the shortest distance we can get to Z? 16. Now 16 is better than 18. So we cross off the old one and then replace it with 16. So when we visited G, Z here is actually better. So we actually have found a shorter path. And the next step we do, we have to visit Z. That's anyone left. And as soon as you visit the end node, which is Z in this case, then you can just stop the algorithm. Essentially, as soon as you visit it, that means, well, that number is definitely the shortest distance to that. So as soon as you visit the node, that's the shortest distance to that node from the starting point. That would be stop. And so the shortest distance then from A to Z is 16. And if you follow it, and as you went through this, you could keep track if you wanted to, but the way we did it, just reminding ourselves, was we did A to C, up to D, down to E, and then G to Z was just the other way around. So that's the order that we sort of did that path in. And again, you can keep track. So, I mean, I've only just visited the nodes, but when you sort of did the nodes, work at the number, you could also keep track of to get this number, where do I have to come from? So, for example, when I changed Z before, so the 18 corresponding to come from F before, there's 16 corresponding to coming from G before. So you keep a track of that if you wanted to. And so a slight variation would also tell you what the shortest path actually is, or just the number. You can do both quite easily. And in doing so, you notice that we've actually worked out the shortest distance from A to every other node at the same time, for that matter. But Z's the one we're curious about. And so this is it's important to know what numbers represent, and that normally helps you out. So just trying to see what it's trying to achieve. And once you try to understand that, then it's not too bad to work out. So the last sort of algorithm we've done, or problem with top we've done, is called a minimal spanning tree. So I'll just finish off with that one. So it's called a minimal spanning tree problem. Can't spell ing very well today. Okay. So pretty much how it arises in different ways. So there's I've got it in the assignment. So the problem in the assignment was trying to make it practical in terms of sort of posting networks out, but we've got a more natural problem to make more. This one here is you've got a bunch of places you want to connect up. So whether it be buildings on a campus, etc. And you know that I want to connect them all up physically. So like wires underground or wires overground or roads or etc. And it's going to cost some money to do that. And so you estimate the costs would be to connect each of the different nodes. Now some things are just not going to happen. So there's A to D. I would never do that. It's not really possible. Well, the natural way to go from A to D would be to go to vice C. So there's no point putting an extra cost in there. So these are all the costs that are plausible. And you go, well, I don't have to build a whole network. I just have to build enough of the network for me to get around. So in order to do that, all you really need is a subset of the graph which spans the whole thing. And the smallest graph you can get which spans the whole thing would be a tree. And so we were looking for a minimal spanning tree. And minimal spanning trees exist so long as you've got a connected graph. And so there are two common algorithms to do this, so Kruskall's and Prim's algorithms. So I'll do just one. So I'll just look at Kruskall's. So they both start the same sort of way, and that is they pick the edge, which is the smallest weight as a starting point. So what I'm going to do is I'm going to keep some working over here. This is my edges added. So the one with the smallest weight is what? So, yep. So E to B would be the smallest one. And again, I'll do it all in place here, but it might be easier sometimes just to draw it sort of separately. So with Kruskall's algorithm, the process is to just keep picking the next cheapest edge every single time. Well, almost. The exception is keep adding the cheapest. However, we want a tree. So we want to make sure is if you keep adding the cheapest edge, just make sure you don't get a cycle happening. So Kruskal's is just keep adding cheaper ones, but avoiding cycles. So the next cheapest would be what? What's the next cheapest? Yep, D to F. Now that doesn't cause a cycle, so fine. The next cheapest after that is C to E. Next one after that is the F to B here. And nothing's causing cycles so far, so we're all okay. The next one to add would be D to B. So I'll just add that in for the moment. You go, hold on a sec. That causes a cycle. So that means that I get a triangle going all the way around. So therefore I can't do that one. So I just put in brackets. D to B causes cycle. So we have to exclude that one. So you can't do that one. So you have to be the next one. The next one will be 30. And again, if you do E to F, that would also cause a cycle. So I can't have that one either. So I have to do 35. So that would be the C to D. But again, that would cause a cycle. So not much lucky. So as a matter of fact, the only way of not causing a cycle now is basically you have to choose at least one of the ends of the vertex would have to be not touching what we've already got. So if both of them are touching what we already have, we're going to get a sort of cycle happening. So when we do C to F and E to D, they would also cause cycles in similar sorts of ways. So the first one we actually get, which we're not getting a cycle, really is this 50 over here, which is A to C. Now, how you go with Kruskal's algorithm, you keep doing, so I'm just keeping adding edges, just going cheaper, so it's a greedy algorithm in that sense, making sure we avoid cycles, and we stop once it's connected. So in this concise time, we've managed to visit every single node, so we've got every node, and all the graph is connected. So that would be a minimal spanning tree. And then the cost of this, so if I want to know what the guy wants to know is how much is it going to cost to connect everything, we add up the numbers. So 50 plus 15 plus 5 plus 20 plus 10. So 30, 35, 40, 50, 100. Whatever units it is. So probably thousands of dollars or something like that is a way of doing it. So you've got to make sure you avoid cycles, and you've got to know when you need it to stop, etc. So Prim's algorithm is a little different. So it still would start with the E to B length, but instead of picking any edge anywhere all over the place, it always picks edges which are connected to what we already have. So you're growing from the E to B, growing out. And you'd always pick things which are the cheapest from what you currently have. So doing it much quicker. Prim's algorithm start with this one here, the cheapest one that's growing out from that. So one edge connected to one not would be the 15 next. The next cheapest growing out from what we have would be the 20. The next cheapest would be the 10. And the next cheapest growing out from this, and again, when I mean growing out, it means one edge touching with what I've already got, and so any edge, one has to be touching what we already have, and one touching what we don't have. And so the next cheapest going out would be this one here. So that would be how the order you get for Prim's algorithm. Now I'll show no working, which is not very good for an assignment. You can see in this case, Prim's algorithm gives you the same spanning tree, which of course has the same cost. There may not be a unique spanning tree. The costs would all be the same for all of them. So if there's lots of them, there'd be the same costs. And so the algorithms might give you different ones. You really notice that the main reason where you get differences is when you have choices. So sometimes you might have a tie. Um, so maybe there's two edges with the same cost. Then you can pick either or. Up to you which one you pick. And that's where you normally get more than one possible answer cropping it from. So that's just an overview of trees, looking at how to traverse them, and just looking at some of the key algorithms we did for weighted graphs. So that should be enough to then now go on to doing assignment 3 and having a go at that and submitting it by whatever its due date is. So 23rd of September. So in about a week's time. So if anybody has questions about that, please fire away, discussion board or forums as you feel appropriate, and make sure we can get through this. And as I said, I encourage you to do enough working so I can understand it, what you're doing. And so either doing multiple pictures or at least clearly identifying on the side here what you've done at each point in time so I can keep track of what you've done essentially. But anyway, thank you very much for your time. If you've got any other questions now, Dylan, you can fire away. But otherwise, we'll finish it up there. Okay, awesome.